Hey, what's up, guys? Captain's log, stardate 91238.25. Yes, I'm actually using a calculator here for the stardate. And today we are talking about the Hyperloop. So I am inside today because I rode my bike to work, so I didn't actually drive my car. Otherwise, I would have did this kind of in the traffic and probably not been as concentrated. So I saved this for when I could sit down and I actually talk this whole thing out. So the Hyperloop. Hyperloop is a design document of roughly 50, 60 pages that was created by the developer or designer of the Tesla Motor Company. He's the guy behind most of the ideas and some of the motor systems that they have in place for Tesla. Some say there's some controversy behind him that he repurposed some stuff that already existed, blah, blah, blah. It doesn't really matter. But so anyway, let's talk about the Hyperloop. I've had a couple of beers, so hopefully I can adequately engineer talk to you guys in a simple way. But so we have a problem in California. We were approved for the high-speed rail system. It was supposed to be over 200 miles an hour, and it's so far it's just sucking. And further, the estimate has been $65 billion to $85 billion to complete. The Hyperloop would be significantly under that. At least that's the idea of the designer here. And he's saying that it would be roughly like $6 billion to $20 billion in there, in and around. I'm not going to get my numbers completely straight because I'm not looking at the design document. I'm really just giving you the high-level logistics of how this works. So don't come and give me all that mumbo-jumbo stuff because we could talk math for hours and it's not going to help get the point across. So don't worry about that. Anyway. And I promise it's going to get funny in a little bit because when I'm actually going to start talking about it, you'll see where this is going. So, travel, as he says, it basically rolls around automobiles, ships, trains, and airplane. Airplanes are the only one that actually changes their altitude to get faster speeds. The reason why we travel at 42,000 feet in and around that area is because we can operate more efficiently. The engines can run faster. There's less air, therefore you have less resistance or turbulence in the engine that can kind of help it go faster. That's not in the case of propeller engines, but jet engines basically work that way. So if you're using a train, trains are generally very expensive because you're on the ground, you have an infrastructure to maintain, and you have the train cars to maintain, and you have all those associated things. And if you're not using a maglev system, you have only as fast as the engine can push at the gravity level that it's running at, and on the material of the tracks to the wheels, and so on and so forth. The Hyperloop would be a revolution in all of these areas. And so let me first get this out of the way. The science behind the Hyperloop is pretty straightforward and would work, and in certain tests and examples you can see this working quite fine. However, the logistics of human travel is kind of what we're talking about here. The Hyperloop would function kind of like, put your thinking caps on for a second. If you ever watched the show Futurama and you've got those pneumatic tubes where the people would fly around and it looks really fast, or the Jetsons, for example, they'd get on a little platform, they'd fly up, fly down, do all that stuff. That's a really simplistic way of looking at the Hyperloop. In those situations, they mostly work in an absolute vacuum situation, and there'd be a pulling, pushing type of motion that was created by some kind of sucking system or blowing system or whatever. The Hyperloop is a bit different in that it's not a complete vacuum, but it's pretty close in that it's basically a simulation of a very high altitude environment. So it's a tube, right? Just like the Futurama, but what the difference is that you would ride in a capsule, and the capsule is very much like, again, think along with me here, a flipped over air hockey table, where the table itself, the part with the little air blowers, is actually wrapped around the frame of the tube. And there'd be a space, a cushion, if you will, around part of the tube, and a lot of the air cushions on the bottom. And that's what the whole unit would kind of suspend and float with very low friction. It's called an air bearing. And how it does that is in two parts. The first part is there's a big fan on the front of the Hyperloop capsule that would suck air in and then blow it down onto the air platform giving it some like low friction barrier like of lift. He called it, what did he call it? Not a membrane, but basically you get the idea. The same thing that causes your little air hockey thing to float above, it would be that, except imagine it in sort of reverse. You are using the air hockey puck to actually provide the lift, and then the tube is kind of like the closed environment in which it floats. Now, if you took the air hockey table and flipped it upside down, provided its own lift, and then put the tube and made the tube very low air resistance by having a very low air pressure, you do that by sucking out a lot of air. You can't get to an absolute vacuum because, as he mentioned, that'd be very difficult, very expensive. The logistics behind that would be a nightmare. But he theorizes that you can achieve about 150,000 feet above sea level air pressure within this tube. Now, to give you some perspective, as I mentioned before, 43,000 feet is about what airplanes travel at. That's when they're most efficient. That's when they're functioning at the best level. If you remember the SR-71, I don't know if a lot of people read about that. SR-71 flew very high and very fast, and when it was on the ground, all of its joints, and it would leak, and it was a mess. There was oil, and it would leak fuel and all that stuff, and it took forever to warm it up. But then once you got it warmed up and you got it up at that altitude, it was just a sports car. All the seals tightened up, everything expanded, and it became just this airtight unit. Well, idea is kind of similar here, is that when you take things up to a very high altitude, either by going up to a high altitude or sucking the air out of a tube and creating an environment of low pressure, not zero pressure or vacuum, but low pressure, you can reduce friction. And by having this kind of like capsule that has very low friction, you can propel it very easily and keep it going just by floating it off the ground and every once in a while giving it a push. And that's what the Hyperloop does, right? So I think it was 70 miles, 20 to 70 miles or something like that. So a distance in space, there would be this linear magnet type drive system. And what it is these linear magnets that are lined up and this very long metal rod or blade, if you will, almost like an ice skate. And the ice skate would come in between the magnets, and the magnets would turn on, pulling, and then turn off, and then in like a segment order, they turn on, pull a little bit, turn on, pull a little bit, turn on, pull a little bit, and that would eventually just power through and suck the capsule that you're riding in, if you will, through. And this is all while the fan's spinning, and the fan's creating lift that applies to the bottom. The fan actually does, along with another motor, power a compressed air container. So it's actually taking the air in, compressing it down, because again, you're in a low pressure system. You're going to need to apply a bit of force downward to create that lift. So it does its own internal compression at a faster ratio than it's pushing out air, and then shoving out this cold, because it needs to make it cold. And again, that's something for that barrier that it floats on, or that buffer / membrane, air membrane, whatever you want to call it. And then it creates that lift. I'm giving you all this stuff, but basically the idea is, if you remember a pneumatic tube system, right? A pneumatic tube system worked on a vacuum principle. Just suck the thing out. Well, this is different in that the vacuum doesn't exist. It's a low pressure thing, but that low pressure thing is assisted by the actual capsule, that little pneumatic tube capsule, actually displacing and pushing out air on its own. So it kind of just air buoyancy, right? If you think about it, it's kind of just floating on a little pocket of air, kind of like a hovercraft works, but in a very low pressure environment. Okay, so hopefully that makes sense. But now I'm getting to what makes this kind of scary to me. And there's a couple things. First, you get in an airplane, right? Every time they go through the safety thing. And what's the scariest thing that everybody freaks out about? They're like, oh God, those air masks. When those air masks drop, we're really in for some shit. Well, the reality is, and there's some scary reality to some of this stuff, and I actually pulled up the numbers. This is something that I'm going to quote verbatim. And this came from airspace.mag.com, and the title of the blog is pretty funny. What happens if an airliner suddenly loses cabin pressure? So the reality is, if I took a gun and shot out the cabin, it wouldn't just blow a hole through it. The bullet hole would make a clean hole, most likely, and nothing, right? Because the air pressure would be able to sustain. The pressurization system's not a problem. But if you had a rapid depressurization, and I'm not talking Hollywood, hole blows out of the side of the wall, chairs are getting sucked out. I'm talking about a hole about a foot in diameter or so, right? A whole foot inside of diameter, it's happened a couple times, will depressurize the cabin. Okay, if you're at, now here's the factual stuff, if you're at 22,000 feet, you have 5 minutes of useful consciousness after this rapid depressurization. That's 23,000 feet, okay? Now 43,000 feet, where airlines are supposed to operate at, you have 5 seconds. 1, 2, 3, 4, 5. You're unconscious. Before putting your mask on and then putting your mask on the child or whoever's next to you. That's why they say put the mask on yourself first, because what's going to happen likely is you're going to try and fumble for your kid's mask. 1, 2, 3, 4, 5. You put the mask on the kid and you're unconscious at that point. That's why there's 2 pilots. That's one of the reasons there's 2 pilots, is that if at any one time one pilot is up, the other has the mask on or loosely connected. I don't know if they use the same ones. I've used one before. It's like they call it the alien, like the face sucker alien from the Alien movies. They push these buttons and it causes this thing to expand. You put it over your head and you let it go and it goes and like sucks to your head. It's not tight, but it's cool. So, okay, 43,000 feet, 5 seconds before you go unconscious. And what did I say earlier? The Hyperloop, the tube, is pressurized to 150,000 feet above sea level. Whew. Okay, so what does that mean? Well, you have a pressurized capsule, right? Pressurized capsule. And if something were to happen, I don't know what, something bad were to happen, you had rapid deacceleration, air mass would drop. Okay, fine. But you have less than 5 seconds now in the 150,000 feet, exponentially almost more than that you have to get this thing on. So you assume I'm going to pass out. Okay, let's say you pass out. Well, there's power systems on board of these capsules that they can maintain this crew. Well, I mean, that's not even really the case either. Gosh, I'm second-guessing myself now. So if you don't get that mask on, you're actually kind of in big trouble. I hope I might be wrong, but I'm now thinking that might be the case. And so now you have a larger problem. And here's where things kind of scare me for the Hyperloop, and I'm getting to it. If you have depressurization in an airplane, what does the pilot do? He's wearing his mask, everybody's wearing their mask, or not. Let's say half the freaking crew just passes out, or the passengers. They just go like this and go back to a level at which there's pressure, an equalization of pressure, and oxygen comes back and everybody can breathe again. That's happened many times. Well, what does that look like on the Hyperloop? If you have this little disconnected capsule and it depressurizes, you have to count on the sensors in that capsule notifying the hub to rapidly depressurize or increase the amount of oxygen in the tube system. So they have to like blow the relief valve or whatever. And then what happens? Well, then, because you've lost all that pressure, now you basically have a capsule that just kind of like comes to a halt. It may be floating, well, it'll float for a little bit and then kind of just drop. At that point, you will probably begin to breathe again and you'll regain consciousness and everything will be fine. But what if it doesn't? What if the sensors don't work? What if the sensors don't call home and tell them this guy, or the capsule is depressurized? What happens then? Well, a couple of really bad things can happen. Now, I'm not so sure on my science of this part, so I'll put a disclaimer up about this, but if you have rapid depressurization in an airplane, you have to come down quick, not because of the returning of the oxygen, which is important because you want people to come conscious again, but the temperature is -60, okay, or 7 degrees below Fahrenheit at that height. I'm not saying that's the case down at this tube level where the Hyperloop would be, but it's definitely going to be cold. So not only do you have the coldness from the changing of the pressure, the removal of the air pressure in the capsule, not only have you gone unconscious, but now you're in this kind of situation where really nobody knows what's going on. So you may still be traveling at 30 minutes, but you may get to your destination and the capsule could be full of dead people, or the people in front of you can't reach you, and their mask, it turns into really a scary thing, right? Because if you've seen the pictures, everybody's stacked right next to each other. So what if two people that are sitting next to each other, they pass out? People behind them can't get to them, right? It's really scary. Then there's just logistical things, like if one of the cars or capsules loses power, at just some point it stops working. Everybody in front of that car, they're fine. They'll just keep going 30 minutes from San Francisco to Los Angeles, vice versa. They'll be at their destination. But if one of the cars loses its power, it'll stop. It'll come to a hovering stop or nothing. It'll just drop. All the cars behind it will have to be notified to stop as well. Now you're back to this whole, well, what if the sensors don't work? And because these are almost, I don't want to say autonomous, but they are their own units. If they're not speaking together, you could very well have a situation where a capsule runs into another capsule doing 700 miles an hour. Whew, that's scary, right? There are brakes, physical brake pads that are supposed to, stick out and slam into the sides of the steel tubing and slow it down. But even still, there's a logistical thing involved with slowing down efficiently, even at a mechanical level. Particularly something that doesn't do it all the time, right? Now, your car comes to a stop. Let's say the car doesn't hit you doing 700 miles an hour, or at any speed, you don't get hit. Now, everybody is backed up. You come to a standstill. Now, a traffic can snarl in California is already bad enough, but even in those situations, even if you're driving a 67 Mustang, you can roll the windows down, you can turn the heater on, and you can keep the engine from overheating, and you can just, wait it out. Or just turn your engine off, and you can sit looking outside at the beautiful whatever. Well, if you lose power to your capsule and you come grinding to a stop, you're stuck there. Now, thank you, Charlotte. Your options are wait for somebody to come in or hope that the overriding system kicks in and the small electric motor, and that's what it says in the design document, the small electric motor will under power wheel the capsule back into home base. Now you're back to like Chilean minor rescue bullshit, because you're basically just going to be limping along on this little electric motor along with everybody behind you that's backed up. They said that they could potentially be loading their capsules every 30 minutes. I'm sorry, every 30 seconds, and it takes 30 minutes to do a full travel from San Francisco to Los Angeles or vice versa. So that in itself just scares the crap out of me. The idea of like a capsule coming into the station, everybody thinks it's okay, you open the doors and everybody's dead. That's a possibility because there's nobody to bring the capsule down to bring the air pressure back. So where was I? Okay, so you've got this little coffin that you're riding in, and if it at any point loses pressure, you could die. That's the final sum game of that. There's also a issue for people who are claustrophobic or have issues with confined spaces or have vertigo or have a tendency to become motion sick. If you can't see the horizon, I get motion sick if I can't see a horizon line or just things. If I can't see out of something and maintain my equilibrium, it'll screw me all up. So that's another logistical problem. Now, I haven't even got to one of the bigger things, which is just, let's say everything works perfectly, and if it were a complete science experiment, then you really wouldn't have a problem with this. And I don't really... They made a comment of it in the design document, and I think it covers what the requirement and the intention of what they're supposed to do is. But, excuse me, if you ever are involved with heavy manufacturing of either highly detailed scientific products, really big stuff, there's a thing called FOD, which is foreign object debris. And that could be a screwdriver that a foreman or a worker left on the line as you're repairing something, and it gets sucked into a machine and it just obliterates a $100,000 machine. Or something gets left in a highly sensitive instrumentation panel and it causes with heat applied, it melts onto the board and the board shorts it out, and you just fried a CPU or whatever controlled configured unit. Processor companies like Intel and AMD, they have extensive and really detailed FOD processes because they're trying to reduce the amount of human material that's brought with humans into where they do the manufacturing. And they really don't want anything left within whatever they're making. Well, imagine a mass transit type of situation where you want to create a hub at which people will walk in, pay money, put luggage into a car, get in the car, and then scurry on down this path. Well, you basically have to create a zero, like, I don't, like hermetically sealed almost tube structure, right, to be able to withstand that. So your tolerances for fraud will have to be incredibly small. If there is someone that goes into the tube to work on something, your tolerance for them leaving tools would have to be like 0. If something ever were to break on a car and get left behind and another car, remember I said it's got a big spinning fan in the front of it, if another car then takes that, sucks it into the fan, it will just obliterate those fan blades. It could be anything. It could be a neck pillow. It somehow gets loose and out and away. It could be an accumulation of even hair. I mean, at a microscopic human level, right? If you're talking about using an air cushion, like, again, now go back to my air hockey table with those little pin-sized holes all over the place. Of course, these holes would be much bigger, but at a certain point, there will be a size of something that can get sucked through that fan that won't obliterate it, that might get jammed into that air thing, and then all of a sudden you're riding along and you dive down, or one side dives in, the other side dives in. You basically get a flat air barrier or air bearing. There are so many things that are promising and cool about this science, but there are so many logistical human nightmares that we just haven't been able to, I don't think that we'll be able to get past. And I don't think I would ever go in this thing. I think the idea of being locked into a bubble that you pray will not depressurize, and the likelihood of it depressurizing would be very small. But if it did, you have a second, maybe more, to get that mask on before you are lights out, and you just hope that they depressurize the tubing. It's not like somebody's driving the capsule and then can release more pressure or more air or whatever. You're talking about no one could know, maybe know. And since they're not going through it with you like a pilot goes through with a plane, there's a very real sense that no one's in control and you're just autonomously writing it out. That scares me. Anyway, I guess that wasn't so funny, but that is a captain's log, and take it easy, guys.